This video is about reaction mechanisms. By the end of this video, you should understand how a reaction mechanism differs from a balanced chemical equation. You should be able to write rate laws for elementary reactions. You should understand the difference between fast and slow steps in a reaction mechanism. And you should be able to determine if a proposed mechanism is viable given a reaction and its rate laws for mechanisms with both slow initial steps and fast initial steps. A balanced equation does not tell us how reactants become products. They do tell us the stoichiometric relationships between reactants and products, but they're generally represented as a single step. Most reactions, however, actually happen in a series of small steps, not represented by the balanced equation. A reaction mechanism is this series of small steps involved in a reaction. Often, throughout the process of these steps, intermediates will temporarily form and break down. Let's look at a little bit of reaction mechanism vocabulary. An intermediate is a species that is not a reactant or a product, but is formed and consumed during the reaction, meaning it may be formed in, say, the first step and then used as a reactant in the second or third step. An elementary step is a single step in a reaction. Elementary steps are important because we can write the rate laws directly from their molecularity or directly from their stoichiometry. Molecularity refers to the number of pieces that must come together to form the product. In evaluating a proposed reaction mechanism, it's important to be able to determine the molecularity of each elementary reaction. A unimolecular reaction involves one molecule being converted to product, hence unimolecular. A bimolecular reaction requires two molecules to collide to form product, bimolecular, two molecules. And trimolecular would require three molecules to simultaneously collide to produce product. Obviously, the chances of this happening are very, very small, since three molecules have to collide at exactly the same time with exactly the right orientation and enough energy to produce a reaction. So this is pretty unlikely, but it is possible. When looking at proposed reaction mechanisms, we'll see a series of elementary reactions, or steps in the reaction. Since an elementary reaction represents the process of molecules colliding to produce product, we can write the rate law directly from their molecularity. This is not true for multi-step reactions, however, where molecules may collide, form an intermediate, which then collides with another molecule to form another intermediate, which then may collide with something else to form product. So multi-step reactions, we cannot write the rate law directly from the reaction itself. So, take a unimolecular reaction. Here we have just one molecule, A, being converted to product. The rate law would be rate, represented by V here, which is equal to the rate constant times the concentration of A. For bimolecular reactions, we have two possibilities, either A combining with B or A combining with A. Here, the rate law would be rate is equal to K times the concentration of A times the concentration of B, or, for this case, rate is equal to K times the concentration of A squared. Often in this class, you'll be asked to determine whether or not a proposed mechanism is a possible mechanism for a reaction. It's impossible to know for sure if a proposed mechanism is the mechanism without lots and lots of experimental investigation, most of which is beyond the capabilities of our lab. However, we can determine just on paper whether or not a proposed mechanism is possible. Let's look at what a proposed mechanism might look like. Consider this reaction. This reaction is experimentally determined to be first order in both reactants, giving us the rate law shown here. A proposed mechanism might look like this. You'll always be given the proposed mechanism. These two elementary reactions here are the steps involved in this overall reaction. Notice first an NO2 molecule combines with an F2 molecule to form NO2F plus a free F atom. Notice that F is not a product in the overall reaction. Therefore, it's an intermediate, which then collides with another NO2 molecule to form another NO2F in a second step. Now that we've seen what a reaction mechanism looks like, let's look at how to determine if a reaction mechanism is viable. There's two requirements for a reaction mechanism to be viable or possible. The first is that the elementary steps must add up to give you the overall balanced equation for the reaction. And the second is that the rate law for the mechanism must agree with the experimentally determined rate law. The rate law for the mechanism will be determined by the rate determining step, or the slow step. A reaction can only go as fast as its slowest step. Your textbook draws an analogy between slow steps and toll plazas on a highway. Here you see that the toll plaza A is processing cars fairly slowly, so cars can only travel down the highway as fast as they're able to get through toll plaza A. Toll plaza B doesn't seem to be slowing them down at all. So the rate of travel down the highway will be determined by toll plaza A. This is the rate determining step, or the slow step. Let's revisit the proposed mechanism from before and test each of these requirements. If we add up these two reactions, we see that our intermediates cancel, and we're left with our target reaction. Therefore, requirement 1 is satisfied. Now let's look at our requirement 2. We know that the first step is the slow step because it's labeled as such, and because this is an elementary reaction, we can write the rate law directly from the molecularity of this step. That rate law would be rate equals K times the concentration of NO2 times the concentration of F2. The experimentally determined rate law is the same. Therefore, this mechanism satisfies requirement 2, making this a possible mechanism for this reaction. Of course, further investigation and study would be needed to confirm this mechanism, but it is possible. Sometimes you'll encounter reaction mechanisms with a fast initial step. This is different than the previous proposed mechanism, which had a slow initial step. Consider the reaction between nitrogen monoxide and bromine gas. It's experimentally determined that this reaction is second order with respect to NO and first order with respect to Br2. It's highly unlikely that this all occurs in a single step, with two molecules of NO colliding with one molecule of Br2 and immediately forming product. It's unlikely because three molecules colliding with the right orientation and the right energy at the same time is pretty rare. Therefore, we're going to need a stepwise mechanism for this reaction. Here's a proposed mechanism. Notice that here the first step is fast and the second step is our slow rate determining step. Based on the fact that we've been writing the rate law based on the slow step, our rate law would look like this. However, this rate law contains an intermediate. This won't work. We can't have an intermediate in our rate law since it's formed and consumed within the course of the reaction. We can solve this problem by expressing the rate law for the slow step without the intermediate. Consider the fact that the first step was an equilibrium step. Here I've written the forward and the reverse reaction separately for that equilibrium reaction. Here's the forward. It would have a rate constant that I've labeled Kf for the forward reaction. And here's the reverse. It would have a rate constant Kr for the reverse reaction. Since we know that this reaction is in equilibrium, the rate of the forward reaction must equal the rate of the reverse reaction. Therefore, I can set the two rate laws equal to each other, the rate law for the forward and the rate law for the reverse reactions. With a little algebraic manipulation, I can turn this into this expression here, which expresses the concentration of NOBr2, our intermediate that we're trying to get rid of, in terms of actual reactants, which aren't intermediates. From there, if I take the constant divided by another constant, I'll just get a new constant. So I'm just expressing this as a different K value. So now I have my intermediate expressed in terms that I can use. Revisiting our original rate law from our proposed mechanism, I can substitute in this expression for our NOBr2, giving me rate is equal to K times NO times Br2 times NO, or K is equal to the concentration of NO squared times the concentration of Br. This actually matches the experimental rate law. Therefore, we know that this proposed mechanism is viable. So, what's the moral of this story? When a fast step precedes a slow step, we can substitute the concentrations of the reactants forming the intermediate for the intermediate itself. Revisiting the example we just looked at, here's our proposed mechanism. The rate law from the slow step would be this. However, since we know that the concentration of NOBr2 will be equal to the concentration of NO times Br2, we can substitute that in, giving us this rate law. Some important notes about mechanisms that were mentioned during this video that you really need to consider. First, these are proposed mechanisms only. We can only determine if a mechanism is possible by inspection. It takes experiment to confirm if a possible mechanism is a true mechanism. Often these experiments proceed by trying to detect the proposed intermediate. That's a common way of doing this. And secondly, rate laws for the overall process cannot include intermediates, hence the need to substitute in should our slow step include an intermediate. Here's a sample AP question to try on your own. Pause the video here. When you come back, I'll reveal the answer. Welcome back. The only mechanism here that's viable is mechanism 2, since it both adds up to the target reaction and the rate determining step has the proper molecularity. Notice that you do need to substitute in since the first step is the fast step. So here we've substituted B in for the intermediate M. Finally, let's take a look at the energy profile for a multi-step reaction. In a multi-step reaction, each elementary step will have its own activation energy. These activation energies represent transition states, between which we have the intermediate. It's important to note that the highest activation energy will always correspond to the slowest step, or the rate determining step. That brings us to the end of this video. Let's review our goals. First, we looked at how a reaction mechanism is different from a balanced equation. Then we learned how to write rate laws for elementary reactions. Then we looked at the difference between fast and slow steps in a reaction mechanism. And finally, we learned how to determine if a proposed mechanism is viable by checking whether or not it adds up to the target reaction and whether or not the rate law for the slow step matches the experimentally determined rate law.